Okay, so now let's derive the formula for the average value of a function. We're going to eventually use this result to prove the main theorem in calculus, the theorem that allows us to integrate a lot more quickly, I suppose. But first, let's do an example. We'll use this example to derive this expression. So let some function t, which is a function of time, which is defined from 0 to 24, be the temperature t hours after midnight. And what we want to find is t bar. T bar is the average temperature over the 24-hour period. So, what you could do is approximate it. You could approximate that. T bar is approximately, if you took the temperature every hour from like 1 to 24. Actually, let me cross that off and start that over again. So, what you could do is take the temperature every hour, add up all those temperatures, and then divide by 24 for a 24-hour period. And that would look like this. The average temperature is approximately 1/24th of the sum from 1 to 24 of t, which is f of t. Right? This gives you the sum of all the temperatures at hour 1, hour 2, hour 3, up to hour 24, and take that sum, divide by 24, and there's your average. That would be an approximation. Or, if you want a better approximation, you could say t bar is like, I don't know, we'll do it like 1,000 times a day. We'll do 1,000 temperature readings, add them up, and divide by 1,000. That's going to be a really good approximation, but it's still an approximation. And we want the exact average value. So what we need is an infinite number of these observations. Essentially, we need, for t bar, the limit as n goes to infinity of 1 over n times the sum from 1 to n of f of t. And really it's like f of t sub I. There we go. Right, because in this case, you're doing the average of n temperature readings as the number of readings goes to infinity. And that limit will give you the exact average. But sums are hard to do. Integrals will end up being a lot easier to do. So our goal is to turn this into an integral. And again, the reason that's our goal is that integrals are a lot easier to compute than sums. We have a bunch of rules for integrals that we'll learn next class. It makes them a lot easier to work with. But this can't be an integral yet. Integrals come from Riemann sums, right? The integral from a to b of f of x dx is the limit as n goes to infinity if delta x is constant, times of the sum of 1 to n f of c sub I delta x. Pretty much what we're missing so far is this. We don't have that delta x. This can't be turned into an integral because this is not a Riemann sum. This is not a Riemann sum because delta x is missing. So, one of the first things we do is figure out how to get delta x in there. Now, delta x, or in this case, it'll be delta t, because delta t is the variable, is b minus a over n. Whoops, I'm off the screen. There you go. Delta t, because t is our variable, see, is b minus a over n. In this particular case, b and a are 0 and 24. So it's 24 over n. And what we want is to put this at the end of our expression. So we do. I'll just shuffle some stuff around. We left off right here. We need a delta t there, so we put one there. But of course, you can't just put a delta t there unless you balance it out. Since delta t is constant by our choice, if we put a 1 over delta t out here, we'll maintain equality. So now we have a Riemann sum. We have a Riemann sum as the limit of n goes to infinity. And the only last thing to do is actually kind of reference right here. Delta t is 24 over n. That means that 1 over delta t is the reciprocal of that, n over 24. And when you plug this in for 1 over delta t, you see the two n's are going to cancel out. And it's going to give you a constant 1 over 24. And now we're in great shape, because this right here is the integral from a to b of our function dt. So I showed this for two reasons. One reason is to stress that the Riemann sum is important. Like, the only way to get the expression for the average value to be an integral is if we introduced delta t, because it had to be a Riemann sum. So that's the first reason. Also, this result, which I'm going to generalize. So, for some function y equals f of x, the average value of y is this expression right here. This is the average value of y equals f of x over the interval a to b. This result is going to be huge in the proof of the fundamental theorem of calculus. So that's the second reason that I showed this. But really the main reason is the fact that Riemann sums play a huge role in calculus, and this is one example of it. One last note before we call it a lecture is this result can be interpreted geometrically, like pretty much everything else that we've seen in calculus. Let me show you how. Some loose paper here. Here we go. So if I was to rewrite this, it says that the integral from a to b of f dx is the same as the average value of the function times b minus a, if you just multiply by b minus a. This basically means, or it does mean I should say, if you have any function that is defined over the interval a to b, that this integral, this area, is equivalent to a rectangle with the same base, b minus a, this is the base, and the height is the average value. So if like this was the average value, that right there is like y bar, if you make that the height of this rectangle, it has the exact same area, exact same value as the original integral. Or to phrase it even more simply, any two-dimensional region can be turned into a rectangle that has the same area. You can turn any shape into a rectangle if you keep the base the same and make the height the average y value. And furthermore, if your function y is continuous, this average value is guaranteed to happen somewhere in between a and b. It's actually the mean value theorem. This is called the mean value theorem for integrals. But yeah, so we'll call that a day there.